Let's talk about some pitfalls when you're using LT-spice transient analysis when you're using the Laplace feature of the behavioral voltage sources. So it can be a great thing to use the Laplace transform feature of a behavioral source in LT-spice to verify a filter's functionality. And here's a simple low-pass filter for comparison. We have an RC, and here's a transfer function where the voltage equals something that has an AC source. In this case, it's V1, and then you type out the Laplace transform. And essentially, this is a low-pass filter with, in this case, omega naught is 2 pi. And you just type that out. You run it for an AC analysis, and you can see that this voltage and this match, so well that you can't tell. Now you could subtract these two signals to see how well they're matching, but if you can't tell the difference at this level, when you go to build the circuit, you certainly won't notice a difference. You can get the LT Spice file there. So what about the time domain? Well, you can create a filter here, and then based on the fact that the input has a pulse, step response is what we want, you can just run it in the time domain, and LT-Spice will attempt to do the time domain response. So here we have a step response. I'm not showing the input, and you can see that basically follows the curve very exactly. If you really try to see, you can see a little green here, but given noise and component tolerances of a real filter, that's an insignificant difference. So for low pass filters, first order, you don't. If you're exploring things, you don't really have to make an RC equivalent. But how does second order filters compare? Well, what I have here is an RLC circuit labeled with nodes 1, 2, and 3, and you can create the four major filters from that. So the low pass is coming off of the capacitor. The high pass, we're taking the voltage from node 2 to 3. The band pass from node 1 to 2. And the notch, we're just adding the low and the high pass. Now if you come over here to the behavioral sources, right, the low pass is just omega naught squared divided by the standard polynomial format. The high pass, it's S squared. The notch, you just derive that out. You have S squared plus omega naught squared, which is the high and the low pass. And the band pass, 2 times zeta times omega naught times S will give you a gain of 0 dB at mid-band. And in this simulation, we're changing the damping coefficient from 10, which would be very overdamped, to 1, which is critically damped, to 0.707, which are the Butterworth coefficients, to 0.1, which just made up for underdamped. And you can see I have the parameter omega naught equal to 2 pi. You have to choose something, and since I'm not really making this circuit, I just choose L to be 1 Henry. Then you calculate the capacitance and the resistance, and so really for a second order system, you choose what kind of filter, omega naught, and your damping coefficient. LT Spice file is there. So what do they look like in the frequency domain? Well, here's our low pass, here's our filter things, and you can see that it's so overlapped that you can't tell what's going on. Here's our overdamped response. You can see two obvious poles. Here it's are critically damped, so you got two poles at the same place, and the gain is down minus 6 dB. Here's our Butterworth coefficients. So as there's no resonance here, but the gain is minus 3 dB. And then here is a very underdamped system. High pass filter, it's almost the same thing. All right, overdamped, critical, there's our Butterworth, and there's our underdamped. It's matching very well. Bandpass, you can kind of see the underdamped, the Butterworth, critical, and interestingly enough, the overdamped is the one that really looks like, you know, a classic bandpass feature. And here's the notch, where the more underdamped you are, the more selective it is. But you can see that they all match really well in the frequency domain. So that to design your filters in the frequency domain, you can use those behavioral voltage sources just fine. But what about when you go back into the time domain? Remember, things are tested in the time domain, and our project, Pulse Width Modulated Filter, is a time domain type thing. So let's look at the low pass. So I just ran that original filter, but just ran it for 10 seconds by changing the simulation that I'm doing, and it's almost the same thing. On my screen here, I can see little bits of green popping through, but that is truly insignificant. What about high pass? Again, it's pretty good. Here we start to see some issues, but it's not really having a... I mean, by the time you went and actually made this filter with component tolerances, that could swamp out any differences that you see to some theoretical calculation. Bandpass. Now we've got an issue, is that for the overdamped, right, we can see this whole green line, which is the true bandpass, totally deviates from the blue. So it doesn't work for the overdamped response. But for the higher, for less damping, it seems to match pretty well. Notch, again, this is the overdamped, and there's a big deviation between the two for damping coefficient of 10. But then it gets better. So what's a designer to do? Well, I would design a filter transfer function. You know, you can use Python or come up with your own coefficients, and you can choose Butterworth or any kind of filter that you happen to be doing. Then to verify it in LT-Spice, create a behavioral source and make sure that the filter is properly designed by looking at the Bode plot. Now to check it in the time domain, well, the low or the high pass response seems to work. So chances are, if you're doing a high or a low pass filter, and then you go into the time domain, it'll probably work. Notch and band, it looks like the overdamped responses deviate quite a bit. So it's probably better to make an RLC analog of the filter you want to check in the time domain. Now that doesn't mean you're going to make an RLC filter. It's just you're trying to simulate the time domain response of a second order notch or band. How it ultimately gets implemented, different story. Now then you would move on to op amps. And then any differences that you see between the RLC analog, meaning it's just a behavioral model using RLC components, any differences you see at that point would be due to the gain bandwidth, or there's higher order poles in the op amp transfer function, or non-linear, non-idealities in the op amp. Now, it seems that unstable systems, these you need to use an RL or C analog to work at all. For instance, if I needed an oscillator, with these unstable systems, right? This has a positive pole, it's exponential increase. This doesn't work in the time domain if I use a behavioral voltage source. And this should be an oscillator in the time domain, and it doesn't work. So if I wanted a positive pole, I can make an RC circuit with a negative resistance. That'll simulate, right? Even though a negative resistance doesn't exist. And you can do an LC circuit with initial conditions to get an oscillator. That's pretty much what the people who make LT Spice tell you to do. Happy designing.